And remember, what is important again is only the PMF, right? The name. Some people, in some books you find these are examples of random variables. They are not really examples of random variables. They are really examples of PMFs in some sense, right? So we are only looking at, we are giving the PMF the importance. Right? The PMF is a model for as a probability model, and the X is just this. The capital X is just something, the name we are giving to that random variable which takes values, right? Just for convenience, right? So what are the important examples? We start with, I'm going to number them. The first one is the simplest one, right? The Bernoulli PMF is the simplest and more, right, non-trivial PMF that we have. So what is it? The basic the most simplest PMF needs to have at least two possibilities, just like head tail, right? So instead of head tail, we are going to call it 0, 1. Okay. So here omega x is basically 0, 1, right? And px of 0, or right, px of 1 we say is some number p. So this PMF is parameterized entirely by this number p, which could be any number between, actually in the degenerate case we are also allowing it to be to take the extreme values, right. So obviously px of 0 must be what? 1 minus p. So note that, right, I am not going to keep writing this again and again, right. The convention is to let this number small p, or the letter p denote the probability of 1, and 1 is almost always identified with either a head or with success, right. 0 is identified with tails or failure, right. So that we will keep that convention for the rest of the course. Okay. So this is right, you can't get anything simpler than this. Okay. Anyway, so the next is we have already seen the binomial PMF. Here omega x is the set of integers. Let me see which number letter I used here. I used, did I use capital N or small n? Okay, I will use small n, lowercase n. So where all did I use capital N in the past? I guess I used it for the receiver number of endpoints, but here anyway we will stick to small n, right, lowercase, right. And what is px of k? What is px of k here? K for any integer between 0 and n is what? N choose k, p to the power of k, 1 minus p to the power n minus k. So this is valid for 0 to n. We have already seen this model, derived it in the context of k successes in n trials, right. Except now that we are giving it giving that number of successes a name, x. X refers, now you can now directly say what does x stand for? Number of successes, right. Okay. So that it's complete now. And of course I think we have already seen the fact that this is satisfied, right. The probabilities obviously do add up to 1. So what is the shape of this PMF, by the way? We have to now, here there is no big issue in looking at the shape because there are only 2 points, but here the shape is important to understand, right. What do you think is the shape of this PMF? If you plot those numbers as a sequence, now we have a discrete time sequence here, if you think of it as, in that sense, right. We have all studied DSP, so we know what sequences are like. So if you plot this, what does the envelope of this PMF look like? It's not necessarily always close to a bell. It's close to a bell. The answer is it's bell shaped, but it's not really bell shaped for small p or large p, p close to 0 or p close to 1. Okay, I have to make again note that this p is typically is not exactly 0 or 1, because you have some degeneracy if you push it exactly to 0 or exactly to 1, right. So right, if you say it's exactly 0, then that means a success cannot happen at all, right. If you look at this, so I mean, okay, so this p, you don't want this p to be this factor to be either 0 or this factor to be exactly 0. So therefore we put p between 0 and 1, but you can make this p arbitrarily close to 0 or arbitrarily close to 1 here, right. So at those extremes it will not really look like a bell shape. So it looks like a bell shape only for p around half, right. So for p equal to half we get bell shape, and we assume that n is fairly large, right, more than 20, 30, 40, whatever, right. P around half, right. So if p is very close to 0, for example, what what kind of a shape will you get for p tending to 0? I think, let me draw it here. Where do you think the probability will be concentrated for p, for small values of p? Where will the probability be concentrated? Near 0, right, because you are saying that the probability of success is on any trial is not very high, right, and you are counting the probability of k success. Obviously no success or very few successes are going to be a lot more likely than k close to n, right. So you will get something like, and remember you are not ever going to go exactly to 0, right, so it will be like this. So I am exaggerating this gap out here for especially for large n, but it will be like this. Note that, right, I mean if I substitute k equal to 0 or n, I do not get 0, right, I get some finite number if p is not somewhere in between, right. So but the fact is this peak will occur close to k equal to 0 and the complementary situation for p close to 1, right, that has to happen because of common sense, right. So whatever we get from the maths has to agree with our intuition here. Okay. Then the geometric PMF, that is again something we have seen, right. So here omega x is countably infinite, so we are saying 1, 2, 3. What did we say about this? We wrote it as 1 minus p power k minus 1 times p. Again this parameter p is between 0 and 1, and right, the expression that we have is for these values of k, right. So these are all defined to be PMFs defined on integer sets or integer arguments, right. But as I said here, that does not definitely always the case. If you take for example the average number of successes, if you define something like that, k by n, that will not be an integer, but you will still get a PMF, right. Each of these values will get divided by small n, and you will inherit all these probabilities without making them sit on any integer grid, right. So you should not think that omega x is always some collection of integers, no, right. I think we have said it right from the beginning that they can be any real numbers, right. Okay, so we have in the geometric case we have this very important PMF, which again as we said earlier is represents the number of times you keep trying till you hit the first success, right, in a repeated sequence of trials where each trial can have success probability p, right. We have done this. Okay, so once again I leave it to you to think, this is basically an exponential sequence, right, in the language of DSP. So px by itself is an exponential sequence. It's an exponentially decaying sequence, right. And I think we have all learned to love these sequences from our DSP days, right? A power n un, except that you are starting from 1 and not from 0. But some textbooks also start from 0. If you start from 0, that means what are you doing? You are actually counting the number of failures before the first success. So if you redefine it that way, you can start from 0. But that is a little less common than this, right. To start, most commonly we start from 1. So these are simple PMS that we have already sort of seen, right. Then let me look at a very interesting PMF for those of you that may not have seen it explicitly, the Poisson PMF, right. Let me write it here, then we will continue there. Now in practice, right, certain counts of electron emissions, telephone calls in some interval, basically, right, the way in which this PMF has been observed to arise in practice is the number of times something happens, right, in a certain time interval. Okay. Again, I do not want to get too much into the history of this PMF and where all, but let me just briefly summarize, right. Right from the 1920s, when people studying radioactivity, when they looked at the emission of actually even earlier, I guess, right, but they started counting them using Geiger counters about 100 years ago, right. So what they did was they observed the number of emissions that were happening over a long period of time, and they partitioned the time interval into smaller time intervals and looked at the number of emissions that happened in any particular time interval, and they found that there was a statistical regularity about this. See, each interval had a random number of emissions, but overall there was, right, if you looked at the you could say, you meaningfully talk of the probability that there would be 0 emissions or 1 emission or 2 emissions like that, right. So, so that was the birth of the Poisson PMF, right. And then the same model was also, again I do not have obviously any first hand evidence of this, but the number of telephone calls in a particular interval, that was in the pre-cell phone era. Now I am not sure, right, if it is still Poisson anymore, right. But anyway, so but there is no doubt that the Poisson PMF continues to be a practically very important model. Okay, and I hope that you people, if you study this queuing theory and so on, you will definitely encounter this model again. Okay, so in this course we will of course make a lot of use of this model without any reference to what it actually means, right, like most other things. Okay, so what do we have? What is omega x in this case? Again, the bunch of integers, but now we start from, where do we start from? We start from 0, right, because nothing, it is also 0 is also possible, only negative things are not possible. Okay, so we start from 0 and we let the numbers right go without bound. There is no upper bound on this. And then what is Px of k? Again, since we have only now integers here, I can just write Px of k. There is now a very important parameter called non-negative parameter called lambda, right, which is called the rate parameter of the Poisson distribution, right, and the value of that rate parameter lambda is crucial, right, and it can be any non-negative number, again going all the way from very close to 0 to very high, and the nature of the Poisson PMF is fundamentally different whether you are looking at small values of lambda or large values of lambda, right. So what is it in terms of lambda? It is e power minus lambda to the power of k by k factorial, right, for k equal to 0, 1, 2 like that. So these two, in fact, Poisson and geometric, are our first introduction to countably infinite sets, right, I mean where we are defining a PMF over a countably infinite set of numbers. And in both cases, right, you notice that as k goes to infinity, the Px of k must go to 0, or otherwise it cannot add to unity. So what is the sanity check here? How do you ensure that this guy goes to 1? So let me continue here. Lambda is strictly greater than 0, right, it's the so called rate parameter. Of the Poisson PMF, right. All right. But how do we ensure that this is going to happen? Is this true? Why is it true? Because you have the exponential series, right? So this is nothing but this e power minus lambda turns out to be the normalizing term, right? Because this quantity here, everybody knows from the study of the McLaw series that this must be e power plus lambda, isn't it? So this is clearly unity. So once again we are using this right, the factorial. For the factorial notation, k factorial is k with a bang, right, exclamation mark after it, right. We will stick to this notation for factorials. It's the international notation, so we don't want to use anything else, right. So please stick to that, right. Okay, so clearly this is valid, right. So we have a valid PMF, and all these numbers are obviously positive. None of them is negative, right. There is no way that this quantity here can ever be negative, so that is also trivially satisfied. The important thing is the shape of this PMF, right. That will tell you exactly where the probabilities are concentrated. Where are they concentrated for small lambda and for large lambda? For small lambda, again you get something, what you saw for the binomial. Small values of k are much more where all the probability in fact are sitting. In fact, you can actually simplify this, right. If you say lambda is so small that you can actually ignore all the terms for k greater than 2, because lambda power k, this, if you take lambda equal to 0.01 or something, that squared or that cubed is right. People often ignore all those terms. They just look at only 0 and 1, and then as you keep increasing lambda, what happens? The whole character of the PMF changes, right. So for small lambda you get basically just something like this. Px of 0 is going to be the largest. What is the value of Px of 0? Lambda power 0 is always equal to 1, right, no matter how small you make lambda, and 0 factorial is always 1. So these terms are always, I mean, they become 1 for k equal to 0, so you have only e power minus lambda. For small lambda, this e power minus lambda is what? You can sometimes replace it by 1 minus lambda, right. And in fact I should in fact blow it up just to show you that, right, I cannot even have with this kind of a pk curve, lambda is actually extremely small, right. There is no point in saying this is 0, 1, 2, 3, 4, 5, it's like that. So right, the PMF is going to 0, will go to 0 so fast, right, that you don't even want to look at it for even for k greater than 2 or 3 or whatever, right. It's in fact very heavily concentrated around 0 and 1. As I said, the limit is just taking the two values, just 0 and 1 itself, right. And for lambda equal to 1, if you put k equal to 1, for example, you get lambda here and you get this e power minus lambda. If you write as 1 minus lambda, so 1 minus lambda times lambda, you approximate that by just lambda, because if you throw out lambda squared, you just get that, right. So 1 minus, so you can think of this 1 minus lambda for 0 and 1, that is also like a Bernoulli distribution, but it is a limiting case of Poisson distribution as lambda becomes very small. Okay, so what happens when lambda is very large? So this is small lambda going to 0, for large lambda going to 100 or 1000 or whatever, that is also possible physically, right. There is no reason why you don't encounter such large lambdas in practice. So now what happens is, what do you think happens? It becomes very much like a bell-shaped curve centered at lambda. Now I cannot look at individual numbers anymore. I have to look at I have to draw an envelope like this. Now lambda equal to 0, k equal to 0 will have very small probability. You go back, this e power minus lambda will effectively kill all the probabilities close to 0. So You will only get significant probabilities around k equal to lambda, and you can, for the sake of argument, you can say lambda is an integer. There is no reason why you should be very, you should cut any, should be very whatever about it, right, general about it. You can say, okay, what happens if lambda is 1000? Surely you will get k equal to 1000 here, right. So this is a kind of PMF. This is how the PMF transforms from small to large. In the binomial case, you do not have such a large spread, simply because that number, the parameter p for a fixed n, is only going to vary between 0 and 1, whereas here you can get decades of variation. When I am saying decade, I am talking of 0.1 to 1000 lambda, that is so many decades, right. What is a decade? A factor of 10, right. So, so Poisson again is a very important practical model, right, and this formula, this px of k e power minus, so please remember this, right. I will expect you people, I am not going to give this one formula, I will expect you to remember, along with the binomial expression, along all of these things you should be able to, you should remember. So binomial Poisson connection. So this connection happens when, start with binomial PMF, right. In fact, this is a notation which is often used to describe this PMF. You just say it's binomial and you put n comma p, the two parameters of the binomial distribution, right, n and p. You write them, and similarly this will be Poisson. How do you call this? You call this Poisson lambda. Right. So you start with n comma p, some, right, where what? N is very large, n goes to infinity, small p goes to 0, such that np goes to a constant lambda, independent of, or np is lambda is like p equal to lambda by n type of arrangement, where n times p is doesn't change with n or p, right. Then it turns out that the binomial PMF, instead of being a two parameter PMF p comma lambda, converges to a single parameter Poisson lambda PMF. Lambda is now finite, not, right, is not going to 0 or going to infinity. So we have a finite, let me write that also, where lambda is and p is finite, some real number, obviously positive. Then this binomial PMF actually, right, the p, if I say p binomial, now I am not going to put a subscript for a random variable, I just put the subscript corresponding to the PMF itself. P binomial of k, right, tends to p Poisson of k for all, I mean for most cases, for k equal to 0, 1, 2, it does not matter, right, because k can go as large as n, the upper, but in theory, right, when n is very large, so therefore there is no, usually there is no conflict in writing it like this, because k, in theory of course k cannot go larger than n, but n is very large anyhow, right, so you just simply put 0, 1, 2. So this PMF parameter, this is a what? This is Poisson lambda. These probabilities are taken from the Poisson lambda PMF, where lambda is exactly given by NP. Have you people seen the proof of this? Yes. Okay, so we can skip that, right? So please go and you can look at the demonstration of this is a very simple thing, right? It just comes from basic exponential, right? The properties of the exponential, the numbers themselves, right? E power Yes. You seeing it now? Is this okay? So where is the property coming? Let me just say one small thing about it, right? How do I, for example, show that Px of 0 or P of 0 converges? Take that simplest of that's the first probability itself. E.g., what is P binomial of 0? With NP, what is it exactly equal to? Please, let's come back to, right? I hope that I mean I'll write it and move away so you can see what's happening, right? 1 minus p whole to the. Now I want to now bring in lambda into this. What do? I write this as 1 minus what is p? Lambda by n, power n. What is this? What happens to this is n goes to infinity, but fixed lambda. It goes to e power minus lambda, right? This tends to e power minus lambda as n goes to infinity. So 1 minus lambda by n whole power n is basically why you get this convergence, and then you can prove it for all, you can show it, show the convergence for all other n also, or other k, right? So the n goes away, the p goes away, all you're left with is lambda. So it's like a pointwise convergence, right? When I say this converges to this, all the probabilities magically or whatever, not they mathematically, I shouldn't say, you shouldn't use the word magically, they mathematically they arrange themselves so that the Poisson distribution very closely describes this. What is the advantage? The Poisson distribution uses only one parameter lambda, it does not care about n. The n is not very important, right, because n is a large number and it can be 1000 or 10,000, does not matter at all, and anyway those probabilities are very small. So again here we are going to, depending on the value of lambda, the probabilities will concentrate in some, and lambda is typically not that large, right, in this situation, right. Okay, so I think you've seen, right, so I can move on here.